four-hands work, four-hands paper about number theory without mathematics. Let me make a very short presentation about our guests. Uri Nodelman is a senior research engineer at Standford University and senior editor of the Standford Encyclopedia of Philosophy, PhD in computer science, specialist in Bayesian networks, with several publications, papers and books, and a nice paper to mind. Edward Zalta is also senior research scholar from Standford University, principal editor of our beloved Standford Encyclopedia of Philosophy, winner of the Barwise Prize and the Covey Award, author of 2 books and around 50 papers in topics like formal ontology, philosophical logic, philosophy of mathematics, computational metaphysics, and philosophy of religion. So everyone is welcome. Let's hear our guests, and then we'll be ready for questions and comments. Please, Ed.
Thank you very much, Walter. I hope everyone can hear me. Let me thank everybody for coming. Today I'm going to try to improve and extend on some results that I published earlier, and I've been able to improve them with the help of Uri, and we've been working on this for a while. So I will have to try to get through the stuff that's already been published quickly in the first part of the talk, and then I'll try to get to the latter part of the talk, and I'll set my alarm so that I don't talk any more than an hour. So the setting here is that the standard view of doing mathematics, or number theory at least, is that for there to be a proof of an unending series of numbers, you have to invoke either mathematical primitives or mathematical axioms or an axiom of infinity. Clearly, you do this in Dedekind piano axioms. You have 0, number, and successor as your primitives, and you have, in second order PA, you also add plus and times as primitives, and you have all the axioms that govern those primitives. Some people like to use second order logic plus Hume's principle, but there again, you've got the number of f's as a primitive, and Hume's principle itself is a mathematical axiom. Set theory requires, if you want to derive the numbers in set theory, well, you still need primitive membership, and you need an axiom of infinity. Principia used an axiom of infinity. Frege arithmetic, which Boulos based a number theory on, requires a primitive notion of a number and a primitive claim called numbers, which uses his eta relation. Third order logic has been used by Harold Hodes with a potential infinity in order to get the number series going. And Neil has used mathematical operators with introduction and elimination rules for those mathematical operators, as well as a potential infinity. But our goal is to derive these Dedekind piano axioms and second order piano arithmetic without any mathematics or an axiom of infinity. Now, there's an additional issue that we have a secondary goal. Frege's method is to define equinumerosity in the usual way of there being a relation that maps every f thing to a unique g and every g thing to a unique f. And then you introduce the number of f's to represent the equivalence class of all the g's that are equinumerous to f. And then you either assume Hume's principle or derive it from numbers in the way Boulos did. But in addition to the usual well-known problems like the Julius Caesar problem, the bad company objection, Frege's method doesn't adapt to a modal setting. The equivalence classes of equinumerous properties change from world to world. So Frege's method yields different numbers at different possible worlds. Now, I think this problem also affects Hodes and Tennant's work, though I don't know this for sure because I don't know how their rules or their axioms fare in a modal setting. Maybe it won't. But in any case, that might not be a problem for them. But our further goal is to adapt Frege's methods to avoid these well-known problems like the Caesar problem and to derive universal numbers in a modal setting, and of course without mathematical axioms or primitives. To do this, our background theory is going to be object theory, which I've been developing for quite some time now. It uses a second mode of predication, which I say x encodes f, and I write it with x to the left of f. And intuitively, the idea is that abstract objects encode or are constituted by all and only the properties by which they are defined. But they're complete with respect to the properties they exemplify, where that's the usual mode of predication. So unlike Boolos's eta relation, f eta x, the applicability of x encodes f isn't limited to equinumerosity conditions. And instead, x encodes f is governed by two comprehension principles. One for abstract object, which says that there's, for any formula phi that places a condition on properties, there's an abstract object that encodes all and only those properties that satisfy phi, and a comprehension principle for relations that says for any condition on objects, there's a relation which is necessarily such that all and only the objects exemplify that relation if and only if phi. And here phi can't have any encoding formulas so that you can avoid Russell-style paradoxes that you could build out of a property like this. Being an x that encodes a property it doesn't exemplify, if you could build an object that encodes that property, you could derive a contradiction. But object theory does, even with this basis, allows for a version of Frege's strategy for defining and proving the existence of numbers, though the minimal object theory has to be extended in a couple of ways in order to prove the principle of induction and to prove that every number has a successor. So now I'm going to review quickly the axiomatic theory of abstract objects for those who've never seen it before. You start with two kinds of atomic formulas. You distinguish a predicate being concrete. You use an actuality operator, lambda expressions, which are complex relation terms, and a rigid definite description operator. And then you define ordinary objects to be objects that are possibly concrete, and abstract objects to be objects that aren't possibly concrete. That is, an abstract object is not the kind of thing that could be concrete. So then identity is defined. First of all, you define it for ordinary objects, and I say x is E identical to y in case they're both ordinary objects and they behave in a Leibnizian manner. They necessarily exemplify the same properties. And then I define identity simpliciter as either they're ordinary objects that are Leibnizian or they're abstract objects that necessarily encode the same properties. And then you can define property identity for properties, relations, and propositions, but here I'm just going to do the definitions for properties and propositions. Properties F and G will be identical, just in case they're necessarily encoded by the same objects. And this is consistent with their being necessarily equivalent in the sense that necessarily equivalent with respect to the objects that exemplify them, but they can nevertheless be distinct using this definition. And then two propositions, P and Q, will be identical just in case their propositional properties are identical according to the previous definition. So here the P's and Q's range over the zero place relation terms, where Fn on the relation term can go down to zero. Then the theory then uses second order quantified modal logic with S5, which means you get the Barkan formulas, and I derive a rule of Rn which allows for contingent axioms and theorems, because we have an actuality operator and rigid descriptions, and you have to make sure that the principles that govern those don't lead you to derive necessary truths from contingent claims. And I also use the axiom for the substitution of identicals. That's completely unrestricted. The axioms for actuality, the only two that we're going to need today are that actually the case that phi if and only if phi, that happens to be contingent, because you can't necessitate that claim without proving things that will be necessary that you don't want to be necessary. And this is a well-known result. I published on it in 1988 in the Journal of Philosophy in a paper called Logical Truths That Aren't Necessary. And the other action just says that actuality is rigid. If something's actually the case, then it's necessary that it's actually the case. Then I use beta, eta, and alpha conversion for lambda expressions, and any axiomatization of the definite descriptions will work, such as the Russell axiom, though then again, that will be a contingent proof because the definite descriptions are rigid. Then, so second order comprehension for relations in this context then becomes a theorem. You can derive it from beta conversion. For example, here's an instance of beta conversion. X1 through Xn exemplify the property being in X1 through Xn such that phi, if and only if phi. But here, what you can do clearly right away is generalize for all these objects here. You can go for all X1, for all Xn. This whole thing holds, and that's a necessary truth. And so then you can generalize on this term. You get there is an Fn such that Fn holds of X1 through Xn, if and only if phi. So that's how you derive the principle of second-order comprehension from beta conversion. And then one of the main features of the encoding mode of predication is that it's a rigid kind of mode of predication. If any object possibly encodes a property, it necessarily does so. Moreover, it's a fact that ordinary objects, and at least it's an axiom, that ordinary objects don't encode properties and necessarily fail to encode properties. So I don't encode any properties, and my possible sisters, which are going to be ordinary objects because they're concrete at other worlds, they don't encode any properties. And then finally, we have a comprehension principle for abstract objects, which is the one that I mentioned before. So this is all set in a fixed domain modal logic where, in fact, both first order and second order quantifiers range over fixed domains. So now using this, the comprehension principle for abstract objects and the identity definition gives you a strengthened comprehension principle, which says for any formula phi, a condition on properties, there's a unique abstract object that encodes exactly those properties. And there couldn't be two, because distinct abstract objects have to differ by one of their encoded properties. So now you get a whole bunch of canonical, the description Vx, which is abstract and encodes exactly the properties such that phi, now becomes canonical. Any phi you add will yield an object. So here's the Leibnizian concept of y. Here's Plato's form of G. The form of the triangle, for example, will be the object that encodes all the properties necessarily implied by being a triangle. That's not a complete object. It doesn't encode either being equilateral or isosceles, but it does encode having three sides, having three interior angles, and anything implied by being a triangle. Then there's the extension of a property, which encodes exactly the properties that are materially equivalent to that property G. And then you can, for any mathematical object, for example, the null set of ZF, you can treat that as an object that encodes exactly the properties attributed to that object in ZF, where this model theoretic sign there is really in object theory defined in terms of a simple definition. You say that T makes phi true means by definition that in T it encodes the lambda, the propositional property being such that phi. So this is an encoding claim, right? So this is the paper that Ori and I published in mine, where we show how this works for arbitrary mathematical objects. And then you get a theorem schema, which is a kind of an abstraction principle that says, and I'll give you an instance, a look at the instance below it, where L stands for being a logician and let B stand for Carnielli. This says the abstract object that encodes exactly the properties that Carnielli exemplifies encodes being a logician, just in case Carnielli is a logician. So there we've just abstracted out something from a simple fact about Walter, and we've abstracted out a fact about an abstract object. Now, since abstract objects are explicitly introduced and explicitly defined and not introduced by way of double identity abstraction principles, there's no Julius Caesar problem. Identity is defined no matter how an object is presented to you. X equals Y is defined for any object whatsoever. So now what I'm going to do, given this minimal theory as a background, I'm going to explain how I extended this theory in 1999 in order to derive the Dedekind-Peano axioms for number theory. Now, to do that, I want to tell you about the minimal model that Peter Axel came up with of the theory. And in the minimal model, basically you have one possible world, and if you start at the bottom there, you look and you see that you have the ordinary objects in the OR elements are empty, but you do need something called a special object, and you'll see what that does in just a minute. Then you take the power set of that, which means that you're going to get two properties, the property that contains the object B and the empty property, and then you take as your abstract objects the power set of the set of properties, and that gives you 4 abstract objects. And then you map down the abstract objects into this object B. This is going to serve as the proxy for these abstract objects in exemplification claims. And the reason we need to do that is because you want to be able to assert of the very same abstract object that it in both encodes and exemplifies a given property F. So for example, the abstract object that encodes being abstract both exemplifies being abstract and encodes being abstract. But you can't do that in a traditional set theoretic setting, because then you'd end up in a non-well-founded situation. So instead of trying to build a model in Peter's non-well-founded set theory, he encouraged you to build this model in terms of classical set theory. So you map the abstract objects down to a proxy. Then you take the domain to be the union of the set of abstract objects and ordinary objects, and you define, you extend this mapping so that for anything in the domain, its proxy is just itself if it's an ordinary object, and it's the proxy if it's an abstract object, as defined by the first mapping. And then under this condition, all the comprehension principles all turn out to be true. Now, the thing that's interesting about this is it shows that some abstract objects, for purposes of exemplification, will collapse. So that means they will be indiscernible. And in fact, it's a theorem of object theory that there are distinct abstract objects X and Y that exemplify exactly the same properties. Now, they're distinct because they encode different properties, but they're indiscernible with respect to the old notion of predication, namely exemplification. So that means I can't exactly follow Frege's method, where Frege's method is to introduce general equinumerosity between F and G, as we saw before, because given these indiscernible abstract objects, you get a following fact, that there's in fact no property that's equinumerous to the property of being abstract. And if you think about it for a little bit, you can see why, because there's going to be these indiscernible abstract objects that are going to get, you won't be able to build a relation that maps it one-to-one into any property G, because of those indiscernible abstract objects. And I won't go through the proof, but you could look through it later if you'd like. So that means that every property fails to be equinumerous to A bang, to the abstract property of being abstract. And in particular, A bang itself is not equinumerous to itself. So equinumerosity on Frege's condition is not reflexive. So since it's not reflexive, it's not an equivalence relation. So we can't define the number of G's as the abstract object that encodes exactly the F's that are equinumerous to G. But in object theory, the ordinary objects are classical. Equals sub E, that is the Leibnizian condition on ordinary objects, is reflexive, symmetric, and transitive. Moreover, if you've got ordinary objects that are indiscernible, well, then they're identical. And distinct ordinary objects have distinct xeities. That if you have X is distinct, E distinct from Y, then the property of being that thing X is distinct from the property of being that thing Y. So now throughout the rest of this talk, I'm going to use U and V as restricted variables ranging over ordinary objects. And then I'm going to define equinumerosity sub E as, that is, equinumerosity with respect to the ordinary objects, means F and G are equinumerous with respect to the ordinary objects, just in case there's a relation that maps every ordinary F to a unique G, and such that for every G, there's a unique F that R maps it to G, to that object in G. So given that definition of equinumerosity, you get this version of equinumerosity as reflexive, symmetric, and transitive, which means it's an equivalence relation. So using just this much, you get some interesting results. So you can define X numbers the G as the abstract object that encodes exactly the F's that are equinumerous with respect to the ordinary objects to G, and define the number of G's as that object, the X that numbers the G, and you don't get a Julius Caesar problem because now the number of G's has been explicitly defined and identity is perfectly general. You get these nice little lemmas that the number of G's encodes a property F, just in case F is equinumerous sub E to G, and the number of G's encodes G, and you can derive Hume's principle from these definitions thus far. So a natural cardinal will then be any object X such that it's the number of some property, And 0 becomes the number of the property of being non-self E identical. And so now where I use F minus U to abbreviate the lambda expression being a F thing not E identical to U, you can define precedes in exactly the way Frege suggests. And I'm going to take it now that you're all familiar with Frege's definition of predecessor. And then you can define ancestrals using a helper notion of heredity. F is hereditary on R, just in case for any two R-related things, if the first thing exemplifies F, but the second one does. And you can define the strong ancestral and then the weak ancestral of any relation R using these kinds of definitions, and precedes will then work. So the properties of ancestrals are derived as Frege does. And from this, you can then define, as Frege does, that a natural number is any object that stands in the weak ancestral of the predecessor series to the number 0. So 0 becomes a natural number. Nothing precedes 0, and no two numbers have the same successor, given the definitions we have so far. So that allows us right away, we've derived the 3 of the 5 Dedekind-Peano axioms. But to derive the last 2 Dedekind axioms, you have to extend object theory, as I mentioned earlier. The first thing to do to extend it is to assert that predecessor and its weak ancestral are relations. And the reason you need to assert that they're relations is because they're defined in terms of encoding formulas, and so you don't automatically get them as relations. And so when you add this axiom, you of course have to prove that the extended version of object theory is consistent. But once you do add the axioms that predecessor and its weak ancestral are relations, you then get in mathematical induction as a theorem. And then the other thing, so then the remaining Dedekind-Peano axiom is derived by adding one other important principle, and it's based on an intuition that I think logicians already accept, namely that the domain might be of any size. And I know that I've heard that uttered by lots of logicians as a reason why you logic not to tell us what the size of the domain is. And so I capture that principle in object theory with a principle that says, well, if you've got a natural number that numbers the G's, then there might have been a concrete object distinct from all the actual G's. And you can formalize that as follows. If there is an X, X is a natural number, and X is the number of G's, then there's possible that there's a concrete object, Y, which is distinct from all the things that are actually G, all the ordinary objects that are actually G. And from that, you get that every number has a successor, and the models of object theory become infinite. So that's what I did in my 1999 paper. Let me just take a little break. I'm talking for a little over 20 minutes, right? I started at 7 afters, 6 afters. So let me take a quick break here and exit full screen. Let me just go back to, just talked nonstop for 25 minutes. Does anybody have any questions that I can answer quickly? Not objections, but points of information before I go on and tell you what Uri and I did to improve and extend these results.
I have one question. Maybe you are going to talk about that later. But which kind of infinity exactly you obtain by this method? Is this Dedekind infinite, or because there are several definitions of infinity? I haven't talked about infinity yet, and I will later.
I
did. I mean, some moments ago you did.
Well, I will talk about it. I've got some slides prepared about infinity, but right now, all I've proved is that every number has a successor.
Yes.
At this point, is just to put, there's a potential.
It's going to lead us to the infinity, right?
I'm going to now, later with Uri, and well, actually Bernie Linsky and I actually showed that there is an actually infinite number on this, what we've got so far. And Uri and I will rederive that. Okay?
Okay.
All right, so I'll go back and carry on. So now, before I carry on, let me just mention that the one thing that's still problematic well, there are actually several things that are problematic, but one is that the theory I just gave you is still subject to this modal setting problem. That is, given the way I've defined numbers, the natural numbers and the cardinal numbers will vary from world to world, because this definition, x numbers the g's, just in case it's abstracted and encodes exactly the properties f equinumerous sub e to g, will have different objects for different property, will be numbers of different of properties at different worlds, even if that property has intuitively the same number of things falling under it. Because in a modal context, equinumerosity with respect to the ordinary objects will vary from world to world, and so the numbers will vary from world to world, just as in the case of Hume's principle and standard equinumerosity conditions. So I partially finessed this issue in my 1999 by making the number of f's rigidly pick out the object that numbers f at the actual world. But I still have all those numbers at other worlds, and Uri and I thought it would be better if we could build universal numbers. And we figured out a way to do that by just building them at the actual world by using the following new definition of numbers, which has one little change. It says x numbers the g's just in case x is abstract and it encodes exactly those properties f whose actualizations are equinumerous to g, and equinumerous with respect to the ordinary objects to g. Now, to see how that definition differs, what I want you to do is, you won't be able to take in the entire diagram, but look at the bottom square at W0, which is the base world, and look at the property Q. Clearly, Q has two objects falling under it, and the number of Q should be 2. Similarly, at W1, the number of objects falling under Q should be 2. But if you consider the old definition, that number that numbers Q at W0 will be a different number that numbers Q at W1, because at world 0, that number will encode R. But at world 1, it won't encode R, because R only has one thing falling under it. Because on the old definition, that's what the definition tells you is the number of G's. But now, so the 2 at W0 will be distinct from the number 2 at W1. But under the new definition, the same numbers, it will be used to number any two-element property, no matter which world you consider that property at. As long as it's got two elements in it, the same number 2 is going to number that property at that world. So, for example, the object that numbers Q in world 0 and world 1 is the same object. It encodes Q and R in all worlds, because Q and R, their actualizations are the things that have two things falling under them at the actual world. So that's the new idea, and it turns out that with the new idea, almost everything else can be rederived, although in a slightly improved form. And now everything that I'm about to tell you to explain how this all works is in a manuscript that I've not published. It's one of the chapters is now co-authored with Uri, chapter 14, and you can now download that. That's an active link. It's a big file, but you can do it later, and it shouldn't take too long to download. But anyway, the proofs of the things I'm about to describe are now located there. So we rederive similar facts that we had before. For every property G, there's going to be a unique object that numbers it, and you define again the number of G's as the abstract object that numbers G's, where now this is the new definition of numbers. And you get a version of Hume's principle, which says if some object X numbers F and numbers G, if and only if, that is, some object does number F and G, if and only if F and G are equinumerous with respect to the ordinary objects. And you get other facts that now become contingent theorems. So, for example, the actual version of Hume's principle is contingent. It only holds at the actual world, and that a number G, the number of G's encodes F if and only if G is equinumerous to F. But you still get that natural cardinals are any object that for which it numbers some properties. And you get various other principles. That you get the definition of 0 is the same. You get the same definition of predecessor. I could have used F minus U in the last clause there. I should have used F minus U to refine that definition. And you can prove immediately that nothing precedes 0. Now you can still derive all the Dedekind-Peano axioms in the same way that I did before, but Uri and I made some improvements to the definition. First of all, we define the strong ancestral as an actual relation, and we defined a special set of relations called rigid one-to-one relations. Those are the relations R such that necessarily if X bears R to Y, then necessarily X bears R to Y. And it's one-to-one in the usual sense that if X bears R to Z and Y bears R to Z, then X equals Y. Then you can define a genuine notion of identity with respect to one-to-one relations. And that becomes a property in the system because it's defined without encoding subformulas. And then you can define the weak ancestral without encoding subformulas because you can then introduce it using this identity with respect to rigid one-to-one relations. So then Frege's general theorem of induction holds for rigid one-to-one relations, where A is any object and R is any one-to-one rigid relation, and that's his form of general induction. And of course, you then get regular mathematical induction by letting A be 0 and by letting R be the predecessor. So then, so you replace, instead of needing two axioms to assert the existence of precedes and its weak ancestral, you only need one asserting the existence of this relation of predecessor, and then you get the strong and the weak ancestral for free. And so predecessor is now defined as this lambda expression, which we know exists as by the axiom that we just used to replace the previous two. And then you derive that every number has a successor in the usual way using the modal axiom. So those were the improvements we made to what I did in 1999. But now we then extended those results in some new and interesting ways. First of all, our goal was not just to derive the Dedekind-Peano axioms, but to derive full second-order arithmetic. And second-order arithmetic goes beyond the Dedekind-Peano axioms because it has the axioms for recursive addition, recursive multiplication, and it's got a comprehension principle for the properties of numbers. So that's now our goal, to show you that we can actually derive the axioms for recursive addition and recursive multiplication. Now, to do that, we basically have to prove a recursion theorem that says, look, if you build those recursive definitions, then there exists a relation in the system that underlies or grounds those recursive definitions. And to do that, we basically reconstructed the theory of basic recursive functions as relations within object theory. So, for example, we first defined mathematical or number theoretic operations as rigid functional relations on numbers. And so, a relation's functional in the usual way. It's rigid in the usual way, as we discussed earlier. And so now you get that successor becomes an operation. It's just the predecessor relation, because it's now becomes an operation that takes the first argument and maps it to a successor, the first argument being the thing which precedes the second. So successor as an operation is the predecessor relation. And numerical identity now becomes identity with respect to this rigid one-to-one relation of predecessor. So then we introduce constant operations using the usual prime notation to denote the successor of n, and the constant operations then become relations. So, for example, you take and typically a relation that has n prime arguments, but the operation ends up having n arguments. So you take any of those n arguments and you map it to one of those arguments there, and then you get the you fix m to be some arbitrary number, and then the constant operation will then take any n place relation and n arguments and map it to that fixed number n. So then that becomes an area operation. And then you get the projection operations. Here, again, the arity of the projection operations is one more than the arguments of the operation. It takes I arguments, but the arity of the relation is I prime, and it returns the kth argument in that string of I arguments. So, for example, and that becomes defined as a relation. So now we're redoing basically recursive function theory in terms of relations, which is what are primitive in this system. And finally, we get operation composition, and I'll just do the simple case of a relation G composed with H, and we use brackets around the G applied to H to get to define the relation X and Y such that there's some Z such that H maps the first argument to Z and G maps Z to the second argument. And then from that, you get as a theorem that if you've got H and G as unary operations, then the operation G composed with H has exactly the same values for an argument X as G when composed with H of X. And this generalizes to n-ary composition, but I won't go into the details because we don't really need those for following. Well, we really do, but it's a straightforward generalization. Then our approach to proving the recursion theorem has the following parts. First, and I'm just going to do the simple case for that's needed for recursive addition, and you'll see that it will generalize to multiplication and to the other defined recursive functions. So we start with two given operations, H and G, where H is a unary operation. That means it's a two-place relation, and G is a ternary operation. And we inductively define a sequence of unary operations where we call them Fn, where F0 is just H and F of M prime is the composition of G with a projection function and a constant function and Fm. So each of these Fm's in the series is a recursively defined operation with a fixed argument M, and then we define F, which is our recursive relation, as holding between n, m, and as a relation between taking the arguments n, m, and j, and f of n relates n to j, and it's basically identical to j. So that leads us to, with that approach, we can then prove as a recursion theorem that if you've got a unary operation h and a ternary operation g, then there exists as a relation, a binary operation f that's defined recursively in terms of G and H. And that's what's said on the red part is the base case, and the blue part is the recursive case. So the standard recursive definition of addition starts with H and G as follows. H of G is just the projection of the unary argument onto itself, which gives you n, and G of n, m, and j is the composition of the successor function with the projection on the third argument place, which gives you the successor of j, which gives you j prime. And so that's basically what you're going to be reconstructing the recursive definition of addition, because f just becomes f of n and 0, fn plus, f is here addition plus, so n plus 0 is just n, and n plus m prime is just the successor of n plus m. So that's how the recursion theorem helps us to derive as theorems, the recursive axioms for addition and multiplication. So that means now we've got all the elements in place for the derivation of second-order Peano arithmetic. We've got the Dedekind Peano axioms, including mathematical induction. By the recursion theorem, the axioms for recursive addition and multiplication become derived by stipulating the recursive definitions in the usual way. And now for multiplication, we basically get that in the same way as we did before. Here we're using a constant function for the base case, and then we're using addition, which we've already defined, on projection functions to get the usual recursive definition of multiplication. And then the comprehension principle for properties is already a theorem, so second-order Peano arithmetic has been derived. And now I'm going to skip this slide, but there is a relative consistency proof of this whole business. And if anybody's interested in seeing what it is, I can tell you about it in the discussion period. But I'm going to try to end early to leave more time for discussion, so I will just skip this for now and come back to it if anybody's interested. But the theory is consistent, or at least relative consistent to a background of number theory. Okay. Finally, now I'm going to talk about infinity, and this is where a previous result is now going to be cast in a new guise. A previous result is that there exists an infinite cardinal, and you can prove that without any mathematical axioms or primitives. And this was something that Bernie Linsky and I did in a paper in 2006. We realized it was a consequence of what I'd done in my 1999 paper. So note so far, we've not asserted any axiom of infinity. In order to get that every number has a successor, the combination of our modal axiom and the Barkhan formula and the axioms for actuality all jointly yield a successor for every natural number. Why is that? Well, let me just take a quick explanation of why that is here. Let me turn this back on and let me erase what I've got here. So now, basically what happens is if you want to prove that for every n, there's a number, a unique number, such that precedes nm, well, since predecessor is functional, all you have to prove is that there is such an m. And since any number that n precedes is a natural number, all you have to prove is that for every n, there's some object x such that n precedes x. Okay, can everybody read that okay? I hope so. I'm going fast. Okay, so now pick n, let n be, just fix n. And now, what does the modal axiom say? Well, n's a natural cardinal because it's a natural number. So there's some property, whoops, what happened? So there's some property g such that n equals the number of g's. But now our modal axiom kicks in and says, well, if there's an n, if n numbers the g's, then there might have been an object y, which is concrete, and it's distinct from all the objects that are actually g. So notice that it says it's possible. It doesn't say that there is, but the Barkhan formula gives you that there is something such that it's concrete. And then that just means let that be, call that thing B. That means that it's possible that there's a B thing. That means that's ordinary. And it's for all U, it's possible that all the the things that are actually G are distinct from B. But if given that identity is necessary, from the fact that it's possible that B is distinct from all the actual G's, it follows that it is. And so now all we have to do to find the successor of n is to consider this number, the number of this property being I'll just write it this way. The number of G plus B, that is, the number of the concept being a Z such that GZ or Z is equal to E to B. And I won't go through the proof, but the point is you can now prove that that number is the successor of N. Because B is distinct from all the things that from all the objects that are actually G. Now, using that should show you, or I hope will convince you that I haven't used an axiom of infinity, but that it's all the elements of the system combined that are actually getting an actual infinity out of here. So that means that we can now prove that there's an infinite cardinal by considering the number of the concept ordinary object. The ordinary objects now the number of that concept couldn't be a natural number because our modal principle will then yield a contradiction. And I won't go through the proof there, but we can look at it afterwards if you're interested. And this is something that Linsky and I put in a footnote in our paper in 2006. Well, Uri and I recognize that this is an interesting development, and it should be combined with the fact that we're deriving second-order Peano arithmetic. So now we've got not only just a proof of the existence of an infinite cardinal from no mathematical primitives or no mathematical axioms, but further, using another paper that I had published with Dave Anderson, we can show that there's an infinite class, because in object theory can reproduce a weak set theory as follows. Define the extension of a property G, and that's epsilon G, as the abstract object that encodes exactly the properties that are materially equivalent to G. And then you define membership. Y is an element of X, and notice the difference between the membership sign and the epsilon operator. They're distinct. So Y is an element of X just in case X is the extension of some property under which G falls, under which Y falls. So that means there are not going to be any new properties involving membership, because there's an identity sign there, and the epsilon G both use encoding formulas. So you don't get new properties. You're not going to get a Russell class. So you get a weak version of basic law 5, and that yields a flat set theory that gives you extensionality, the null set axiom, the unions axiom, intersections, separation, but you don't get arbitrary pairs for members of the domain, and you don't get a power set axiom or an axiom of infinity. But you can get every property has an extension. In particular, the property of being an ordinary object has an extension. This is the natural class of the property of being ordinary, and its infinite cardinal, its cardinal is infinite, so the extension of that property is an infinite class. This gives us a proof of an infinite class without mathematical primitives or mathematical axioms. And so I'll conclude by just suggesting that we can revise Kronecker's dictum, that we should revise it as follows: God made the numbers of Peano arithmetic, second order Peano arithmetic, and the number of ordinary objects, and all the other numbers are the work of humans. And with that, I'll stop and take questions.
Thank you.
Thank you very much.
Thank you very much, Ed. Okay, very nice and intriguing talk. I hope people have questions and comments. Let me open the discussion.
Oh, I'm so sorry. I forgot to no one reminded me to disseminate the slides. Is there a way can you send files through?
You can send them to me, I think, by email later on.
Oh,
Augusto, can you hear us?
Wait a second here. You can download this. Let me just.
Is it possible to share the slides now?
Yeah. I had no idea. I forgot to do that. I'm very sorry.
Okay.
And so. There you go. See if that link works. Does that link work? Everybody get that link?
Yeah. Okay.
Yes,
Okay.
I opened.
Nice.
And actually, I have an A4 version. Hang on one second. Since you guys are on A4 paper.
The only problem is that I copy myself this link, because later on it may disappear. So I put a note to myself on my board, and that's
Okay.
I recommend you do the same.
I didn't hear that. You got chopped off.
I'm copying the link to myself.
Oh, I see. Okay.
You copy the link to myself. Very nice. So, questions and comments, please. You can raise your hands or very informally, if you like. Don't need to write down in this.
There is a way to ask for speaking, or I can just speak.
Yeah.
You are number one. You offer yourself. Please go ahead.
I don't want to came before others that want to put questions. So okay, I can speak.
Please.
So I have I have three points. First point is a joke, of course, but your last point about Kronecker make me think that you consider that there is God and at Zalta that give us numbers.
Sorry. Sorry, that's not. No, this is not me creating the numbers. They're there. Okay. They're there already.
This is a joke. No, the first real question is really a question to you. It's not an opinion, it's a question.
Okay.
I understand that you need all the logical apparatus that you described in order to have the recursive definition of addition and multiplication. But okay. I was convinced, and I also believe to have done it in something that I did not publish some years ago, that you can, once you have in Frege arithmetic, I don't know exactly your setting, but in Frege arithmetic, when you have the Dedekind Peano axioms, you can define explicitly, without recursion, addition and multiplication. You can give a formula that says that z is equal to x plus y, if and only if a certain property appear. So you think that is not possible? I was convinced that it is possible.
Oh no, you can do it. It's just that you need to show that look. The only way to prove the existence of relations in second order logic plus Hume's principle is to show that there's an instance of comprehension. But comprehension in and of itself doesn't let you use a recursive definition to produce an instance of comprehension. So yes, you can give the recursive definitions of addition, but there's no guarantee that comprehension will give you a relation of the right kind unless you prove a recursion theorem.
I see, but in a Frege arithmetic, you have full comprehension. That should not have a problem. So when you work in Frege arithmetic, you work with full comprehension normally, no?
Right, but I'm just saying that we tried to follow the standard procedure.
Oh, okay. That I see. So you're setting. Okay, that's I see the point. Okay, that was the question that I want. The answer that I wanted.
Yeah.
Okay, now it's clear. Okay, perfect. Okay, now the question. I think your argument was presented quite quickly, and I think that it would be necessary to reflect on it a lot. But I think to have understood and to agree with you that you don't use axiom of infinity in a certain sense. My question is another: whether you cannot, it's not possible to argue that your modal axiom, together with Barkov formula, is exactly in itself an axiom of infinity.
So you think it is? Here it is. I put it up on my screen.
My point is that it seems to me that your modal axiom in presence of Barkov formula is not innocent as you suppose it is, and so we can use exactly your argument in the other way around to show that exactly because axiom together with Barkov formula has this conclusion, this is a proof of the fact that is already in itself this pair of this axiom in presence of Barkov formula in axiom of infinity. So how you answer to this objection that you don't use axiom of infinity because you have already an axiom of infinity under the form of the modal axiom in presence of Barkov formula?
I'm sorry, I didn't see. Which axiom do you think is the axiom of infinity I'm using?
The modal axiom.
All it says is that if there's a number of numbers, the g's, then there might have been something. That doesn't give you the existence of anything.
Yes, but in presence of the Barkov formula with a logic.
Well, there you go. That axiom is not an axiom of infinity because it doesn't assert the existence of anything.
But
an axiom of infinity has got to assert the existence of an actual infinity.
I see. So I put the argument in another way. Don't you think that what you are answering to me, a version of the no-logicist argument for the known fact that Hume principle has not a existential import. By the way, they say it's more or less the same thing that you are saying now. The axiom itself has not a existential import, but when you add it to the apparatus of second-order logic and that they have, it has existential consequences. And it seems to me that something like that could be said also of your modal axiom.
I didn't quite catch all that because of some audio problems. Uri, did you hear what he was saying?
I say, so there is a classical objection to Crispin Wright and the neologicist argument that say that the Hume principle as such has not existential import, but when you connect it with the apparatus of second-order logic with full comprehension, it triggers existential import, and this argument show that in fact there is something as an existential import in the Hume principle itself, even if apparently it is not there. So don't you think that a similar argument can also be applied to your modal axioms? As such, is not an axiom of infinity, but when you put it within the apparatus of your theory, including Barkham formula and all the rest, it gives that, and what you proved can be exactly considered as an argument for that. You proved, in fact, that your modal axiom is not so innocent as you argue for.
Well, first of all, I don't think all Hume's principle says is that if you've got the number of F's and the number of G's, that they're equinumerous, if and only if the F and G's are equinumerous. And they're identical if and only if the F and G's are equinumerous. That's in and of itself not an axiom of infinity. Of course, I agree, and you need the background of second-order logic, and in the context, just the addition of that one principle is what gives you an infinite number of numbers. Now, you could argue similarly that, well, if I've got the Barkham formula, the addition of this one principle gives you the infinity, but in Hume's principle case, there is existence claims on the left side of the biconditional, because it packed into the number of F's and the number of G's, there's already a claim that there is a unique thing which is a number of F's, and there is a unique thing which is a number of G's. But I don't have that in my modal axiom. I don't have an implicit existence claim. I simply assert something that gives me a potential infinity, but not an actual infinity. And you need the Barkham formula in order to, and plus the axioms of actuality in order to make this go through. So there's already existence claims built into Hume's principle, I would argue, because you don't get the number of F's for free. You have to presuppose that for every property there exists a unique number which numbers it. That's built into Hume's principle. So it's already got an existence claim built in, whereas the modal axiom doesn't. Uri, do you have a different answer to this? Or?
No, I understand your point. I see your point. By the way, the volume disappeared in a certain moment. But I think that I got your point, and I see. Okay.
But maybe let me ask if Uri has a different.
I'm not sure to agree with you, but I have to think about it. I see your point.
Yeah. Did you have a different way of responding, Uri?
No, that captured our discussions about it. So yeah.
Okay. Great. Thanks, Marco. That was interesting. Good question.
Thanks to you.
Anybody else? Anyone else? Other questions or comments? Or please feel free. Counter examples.
Did the links to the slides work?
Well, I didn't try them, but apparently
all you have to do is just click on them and see if it opens up.
I tried. It worked for me.
It works for you? Okay, well, if it works for one person, it'll work for everybody else.
Then there's a a higher probability that they'll be working for everyone. I hope. Well, I will make naive questions for a while nobody else has another question. I don't see very clearly. If you have an infinity, that's where my question about infinity is more related to Marco's question. I don't see very much the distinction if you have an infinity or a non-finite.
Oh,
where, I mean, how can it's an infinity?
Unbounded, yeah. No.
Non-finite.
Right. Well, no, the Peano number theory, in and of itself, even second order, only gives you an unbounded number series. It doesn't give you anything that's actually infinite. But we're not only getting an unbounded number series, since every number has a successor, but we're also getting this thing, the number of the ordinary objects, the number of Aubin. And that is an actual infinity and not just an unbounded series of numbers. So it's not just a potential infinity, it's an actual infinity.
But how can you reply to the following question? Is this what kind of infinity is it? Is it Dedekind infinity, or because you need an axiom of choice to compare infinities, right? Or not?
No, the axiom of choice is built in set theory. There's no set theoretic primitives in this system. So there's no axiom of choice that's expressible. This simply says you've got this number, it's a natural cardinal. It can't be any natural number. So it can't be in the natural number sequence. So that's all the theory tells you about it. And of course, what its size is from a model theoretic point of view might depend on the number of ordinary objects there are in the domain. Right now, we know that at least there's got to be something larger than every natural number.
So you say that you have exactly Dedekind Peano axioms, or right?
The Dedekind Peano axioms plus, which gives you the usual 5 axioms, including mathematical induction, plus recursive addition, recursive multiplication, plus comprehension for the properties of numbers. Now, Simpson, in his texts, he doesn't use properties of numbers, he used sets of numbers, but it's just basically a kind of variant. His comprehension principle is for sets of numbers. So he has to add a membership relation, and then comprehension is comprehension for sets of numbers, for arbitrary sets of numbers. But I'm working in second order logic without a membership relation, and comprehension comes for free.
I see. Then it means that you can recover Girdle's axiom of exactly in your arithmetic. Right?
Whose axiom?
Girdle's result.
Oh, yeah.
You can recover it completely, right? Because you are able to do, like I don't know, Girdle codifications and Chinese remainder theorem, or all the kind of arithmetic tools necessary to rebuild Girdle's arguments. Can you do that?
Girdle's. Are you talking about Girdle's theorem or his axiom? Some axiom.
Girdle's
incomplete theorem.
Probability of consistency.
Yeah. I don't have. All I can say, Girdle's theorem, as I understand it, is really a theorem of primitive recursive arithmetic. Is that correct?
Yeah.
So, and you have to remind me exactly. Does primitive recursive arithmetic include a mu operator? Because we haven't defined a mu operator.
No.
Okay. Well, then the theory is subject to Girdle's incompleteness theorem, and you can do the usual kinds of things you can do with second order Peano arithmetic. It's stronger than primitive recursive arithmetic, right?
But
what is its consistency strength, Edward?
That's a good question. I mean, what do you ask? So doesn't Panu have a paper on this? And I don't know all the details. Panu has a recent paper on the consistency strength of second order piano arithmetic and versions of, he calls, so Panu has changed the discussion a bit, because in my article on the Stanford Encyclopedia, I called Frege's theorem just the derivation of the 5 Dedekind piano axioms, because that's the way Boulos and Heck and others talk about it. But Panu in his paper extends, he now calls Frege theorem the derivation of full second order PA. So not just the Dedekind piano axioms, but in addition, a recursion theorem and the addition and multiplication axioms and comprehension. So but Frege didn't actually do all that in the Grundgesetze, as far as I know. That wasn't really. I mean, it's there. You can extract it from the Grundgesetze, but Frege didn't, really formulate a version of second order PA in that respect, right?
But the problem generally arises for anyone who is deriving piano arithmetic in any fashion. Mm-hmm. How can you simultaneously make out that the wherewithal for that derivation is what a logicist or a neologicist would require?
Oh,
okay. So it's got to be analytic in some way. But let me finish framing the question.
Sure.
So you want the wherewithal that is used at a deeper level to yield the piano axioms, whether or not the induction thing is understood schematically at first order or parametrically second order, whatever. Yeah. Okay. But at the same time, you're aware that there's the Gödelian problem about proving the consistency of piano. Mm-hmm. So you want your wherewithal to be as weak as possible.
Sure.
So that you're not, as it were, increasing the danger of inconsistency by that much in giving a logicist derivation of arithmetic.
Sure.
And so I'm wondering whether your formal theory has admitted of any translational interpretation into any other neighboring theory, like second order set theory or type theory, or all those things that, for example, Burgess has anthologized for us at the end of his book, Fixing Frege. There's a panoply of theories there that are organized in this surprisingly linear hierarchy of consistency strengths. And I'm just wondering where the Zalta Leibniz stuff shoots in to that hierarchy. How powerful?
I have not studied the strength of object theory relative to the background framework that Burgess produced or that Panu produced. Okay.
Here's one problem for you, though. The more you say we're doing this without mathematics,
yeah,
the more you're putting yourself, as it were, beyond the legitimate reach of comparative studies of consistency strength, because you're going to say, I'm not in the mathematics game, so somehow I'm immune to being incorporated into this linear hierarchy. I'm just wondering if that is a possible...
I don't see that. I don't see why that should follow. I mean, it's a formal theory, and as such, mathematical results apply to formal theories. I'm just saying that there's no mathematical primitives in this formal theory, and there are no specifically mathematical axioms in this theory, but that doesn't mean it can't, metamathematical studies don't apply to it.
Oh, okay, so that's good. But then it lends a different sort of interest to the claim that there are no mathematical primitives, because after all, if you were a thoroughgoing logicist, you would want to get to those mathematical primitives from your logicist wherewithal. So you would start off without any mathematical primitives, but then through appropriate definitions, you would provide them, you would furnish them, and then you would show that from deeper, more underlying logical principles, through the definitions, you are now getting something that looks like mathematics.
Well,
and I guess that's the situation I have with your account.
Yes. First of all, I didn't actually explicitly defend logicism at this point. I simply argued to defend logicism, I'd have to argue that the theory that I gave is a logic. But I didn't argue that in this. I'm actually working on a paper with Uri and Hannes Leitgeb where we argue this, but I didn't defend it here today. But the main point is that, yeah, all I've tried to do today is show you that I used classical second-order quantified modal logic, which has no mathematics in it per se. I added an encoding form of predication, which is in and of itself is not mathematical, and I added the principle about this lambda expression, which is an ordering relation, which is not mathematical per se. We have ordering relations that can be expressed without mathematics. Just, any partial order can be expressed without any mathematics. You just place conditions on a relation R. And I added a modal claim in terms of things that have been defined. It does use the number of F's, but that's defined without any mathematics. So I'm trying to do what the logicists do, except at this talk I didn't take a final step and argue that the framework is itself a logic.
Right.
I have a follow-up that suppose
hang on 1 second. Before you do, I want to make sure if Uri has any additional thoughts on this question, that he has a chance to speak up.
No, I mean, I was just going to say that on the consistency strength question, it's a good question and one we just haven't looked at yet, and probably one we should.
The follow-up is the following. Suppose that you can successfully argue that your system is logic, all is okay. But let's take for a moment the position where we are. Say that there is no mathematical primitive, but you did not say that your system is logic. So what it would be if it were not logic?
That would just be pure. It would be metaphysics.
Something between logic and mathematics in this setting. Something that is not mathematic but is not logic. So what
it would be? It's metaphysics. At this point, it's the metaphysics of abstract objects, where the metaphysics of abstract objects is all-encompassing over the kinds of abstract objects that people have postulated in the past. This, as I tried to give you some examples, philosophers since Plato have argued for the existence of abstract objects of certain kinds. And I've tried to show that each of those abstract objects that have been postulated, there's a subdomain in object theory where you can reconstruct the principles of those abstract objects and define them using object theory. So at this point, you can think of it as simply a proper metaphysical theory of abstract objects. Now I have to take an extra step, and the extra step to argue that it's a logic is to argue that it's required for any kind of abstract logical thinking. And if I can do that, and this is what Hannes and Uri and I are working on paper, where we can argue that for the to have complex mathematical thoughts and derive consequences of those thoughts, this kind of system is needed. Well, then we might get some way toward arguing that it's a logic and not just a metaphysics. But I didn't argue that today.
Indispensable for reasoning. That's what you think about logic. Logic means indispensable for reasoning.
For reasoning, that's right. What we need to capture the consequences that we in fact draw. I take it there's a body of judgments out there. We draw inferences between statements that we make, and in particular, whatever logic has got to do, it's got to explain the inferences of mathematicians as well as the inferences of ordinary folk. And so if I can then argue that this system explains in a way that other systems don't, the logical inferences that mathematicians make, well, then we've gone some way toward arguing that it's a logic.
Thank you.
Yeah, but at this point, it's just a metaphysics.
So Ed, for a Kantian who thinks that Kant correctly categorized both mathematics and metaphysics in the synthetic a priori box.
Okay.
Yeah. is your theory synthetic a priori?
Yeah, at this point, the comprehension principle for abstract objects is a synthetic a priori principle.
Okay. So now what the logical positivists did was maintain that the logicist reduction of number theory had kind of worked, and geometry had been rendered empirical, so just synthetic a posteriori, if true. And then they kept saying in letters to one another, "Weg mit der Metaphysik," so that you were left just with the analytic a priori and the synthetic a posteriori. Now what's going to happen is that when everyone is convinced that you can do this in terms of your general metaphysics, they're going to go around saying, "Weg mit der Mathematik."
No.
And then you have to tell us whether that box is empty.
No, not at all. Here's why. I actually think that this fits exactly with the Carnapian tradition of logical empiricism. Why? If you remember Carnap's paper from the late 40s, early 50s, where he says he believes in abstract objects and that one can have abstract objects. Why? Because he distinguishes between internal questions and external questions. And he says, you give me the mathematical framework, and the internal question is already solved. Of course, the numbers exist, given the framework of numbers. Of course, sets exist, given the framework of sets. Of course, propositions exist, given the framework of propositions. But Carnap was a semanticist, and the thing that's missing from his account is a principle that says, you give me the framework, I'll give you the right objects. He just assumes that the framework comes with the right objects. But what does that for him? It's only a comprehension principle that it's unrestricted, for which you put in the arbitrary framework and it generates the right objects for that framework. And that's what object comprehension does. It's Carnapian in that exact way. So you can have mathematical objects. I'm not telling the mathematicians away with mathematics. No, I want them to be as inventive and original with new mathematical ideas as possible. But I want to tell them what their language means and what it from a metaphysical point of view or a logical point of view, to show them that, they're not invoking any spooky objects of any kind. They don't need the kind of full Platonic universe that we thought we had. There's a perfectly good explanation in terms of rigorous scientific background principles. That's
something you're really going to have to emphasize when you present this to wider philosophical audiences. because they're going to think that you're like some metaphysician yearning to answer the external questions that Carnap was talking about. So you're going to have to really emphasize that you're working within a Carnapian framework, but that your object theory renders this kind of service within it, or acting on it.
At first, my guess is that people, for example, who hang out at the Foundations of Mathematics list are not going to be as interested in the philosophical questions. Maybe they will be, but I don't know whether I'm not sure. I'm trying to say that. Well, here's the way to think of it. Think of the thing that's missing from Carnap as a meta-ontological framework that gives you, for an arbitrary ontological framework, the right objects so that the internal questions yield an automatic yes. And you answer, do numbers exist? So this is what object theory is kind of is like a more of a meta-ontological framework for analyzing arbitrary mathematical theories. Yeah. So maybe, but I take your point. I take your point that the way to try to convince a segment of the philosophical logicians is to emphasize the connection with Carnap and the logical empiricist tradition. Yes, that's right. Though I still think that at heart there's a group of logicists who will resist that. People who are logicists at heart and who will resist that and need to be convinced by some other means. And that's what Hannes and Uri and I are working on. Yeah. But I appreciate the friendly suggestion of emphasizing the connection with Carnap. That's right. Uri, did you want to jump in about any of this?
That's great. That's great. I'm just taking some notes here too.
Okay, good.
Okay, I have an additional question for you, Ed. Uri. It concerns my attempt to understand the range, the limits of your new theory.
Sure.
I understood well. You cannot do full recursive, general recursive theory, right?
Full
General
recursive.
You cannot do general full recursive arithmetic.
Full recursive. So the one thing we haven't done is added a mu operator.
Yes.
And I don't know that, if I were to add such a thing without defining it, then I would be involved in some mathematics.
Yeah.
But and one area of investigation is to whether that could be defined.
No, I need to understand where it goes. So for the moment, you cannot state full Turing thesis, right?
Okay.
That's something interesting. That's something interesting because you may, in a certain sense, maybe bringing up a sort of a weaker and new theory of computation.
Well, that may be, though. Again, if I were to simply say to get the church Turing thesis, you need to add maybe one thing to what I've given you so far, then I might be willing to add it if a compelling case could be made. Basically, you have to approach this scientifically. You want to see you want to get the strongest results from the weakest set of primitives and axioms. And so I take your point that in the first instance, it would be good to investigate the kind of computational complexity you get on the basis of what we've got so far without going into the full church Turing thesis complexity. Yeah. Is that now? But now I've got to defer to Uri on this because Uri's the computer scientist and knows a lot more about this than I do. Uri, do you have any thoughts about?
I think you've characterized that the way I would. That it's we haven't this is what we've looked at so far. We haven't looked at extending to past that, or to figure out what things might or might not be definable past that, or what things we'd have to work on to do it. I mean, we originally weren't sure we were going to get the recursion theorem out, but so figuring things out, that's part of the work. So
yeah. So for the moment, you cannot even state the halting problem. Turing's halting problem.
Oh,
right,
not
currently.
Yeah, not because you need this little recursion, the me operator. Right. Okay, just for me to understand, I mean, the current development of it.
Right.
Great, thank you.
But I've given the mathematician the tools that they need to state it.
If you're giving everything they do, you're giving them a fair amount of tools.
Yeah.
How much is this sufficient or not? I don't know. I cannot say.
Yeah.
Okay. Okay. Very nice. So we more than 1 hour and 20 minutes now. Anybody else? Please, more comments, questions, or remarks?
Hi. I would have a question. Do you hear me?
Yes.
Okay, perfect. So, from what I understood, it seems that shortcoming of your theory that you can only count ordinary objects, you cannot count abstract objects, right? And
almost right. In the strictest sense, that's true, but you can still count them using the logical quantifiers. You can define the logical quantifiers. There's exactly one x such that phi. There's exactly two x's such that phi. And then you can extend that to there's exactly one abstract object such that phi. There's exactly two abstract objects such that phi. So there is a method of counting them, but you just can't use the natural numbers, which only count the natural world. Yes, so that's...
Okay, but that can be viewed as a weakness of your theory, right? Because we might want to count with and do number theory on the natural numbers, for instance, to count natural numbers, and I think that's the same reason why your set theory, your induced set theory, is, well, as you said, flat. And my question is, first of all, would you think that it would be interesting to have a number theory and a theory of extension that could actually, in some sense, count and have classes of abstract objects as well? And if so, do you have any ideas on how to develop it?
So yeah, look, I did not start off the way I usually do. So object theory has a certain approach to mathematics. And the approach to mathematics is to divide mathematics into two kinds. There's natural mathematics, the things we get from ordinary language, like counting. And when I say, like, the class of insects is larger than the class of humans, or ordinary triangles that you might find, written on a blackboard. And then there's theoretical mathematics. Theoretical mathematics is what you get once you start getting axioms and theorems, or principles. You start laying down mathematical principles. This talk was a talk simply in natural mathematics. What you get from the pure theory of metaphysics at this point, you get numbers and you get sets. But if you want to explain how object theory gives an analysis of theoretical mathematics, which includes arbitrary group theories, arbitrary geometries, arbitrary set theories, arbitrary number theories, well, this is where the paper that Nodelman and I published in 2014 comes in. If you want numbers that count other numbers, well, then you use the Dedekind-Peano axioms or second-order PA axioms as primitive. And you don't analyze them this way. You bring them into the object theory under the scope of their theory operator. So on this slide that I have up here, look in the middle of the page. I take it that ZF is a theory, a particular mathematical theory, and it has a body of theorems. And its theorems can be translated into object theory, and that the theorems for any theorem, you can get something of the form that ZF makes it the case that the theorem holds. And so the null set of ZF there is now analyzed as an abstract object that encodes exactly the properties F that the null set exemplifies in ZF. And then you can do that for any arbitrary distinguished object kappa in any arbitrary theory T. So if you want numbers to count other numbers, well, you have to do it by treating the number theory as theoretical mathematics. And so what I'm suggesting is that object theory still gives you an analysis of theoretical mathematics. It's just that theoretical mathematics is often way more powerful, and you can't give the kind of reduction that I've given in object theory, because object theory is relatively weak in that regard. So in order to get the stronger mathematics, this kind of reduction is not the same kind of reduction as I gave before. Basically, for Peano arithmetic, we gave a relative interpretation of the second-order Peano arithmetic and object theory. But for theoretical mathematics, I don't use relative interpretability as the standard of reduction. Instead, I call these ontological or metaphysical reductions, and that you need to import the theorems of the mathematical theory under the scope of the theory operator into object theory, so that you get sentences of the form in ZF, the null set has F. And then you can abstract from the theorems the properties of the null set and encode them into objects. So that's how I would address your concern, or what you see as a limitation. It is a limitation if relative interpretability is your only standard of reduction, but I don't accept relative interpretability as the only standard of reduction. I think there are ontological reductions that give that show that mathematical language is about abstract objects, and it generalizes. If you'll permit me one further comment, I've just given you the second order version of object theory. There is a type theoretic version of object theory, which generalizes in a simple type theory. At every type, the domain of that type bifurcates into ordinary objects of that type, which don't encode properties, and abstract objects of that type, which encode properties of properties, or encodes properties of things of that type. So that means we're going to be able to actually not only give you an analysis of theoretical numbers, but also the theoretical relations of theoretical mathematics. So membership will become an abstract relation that encodes exactly the properties of relations that are attributed to it, for example, in ZF. That will be the membership relation of ZF. So in particular, the membership relation of ZF will encode this property. Being a relation R that relates the null set of ZF to the unit set of the null set in ZF. So that becomes oops. Did I erase it? Good. All right, so now let me use my pencil. So basically the null set will encode this property of relations, being an R, such that the null set bears R to the unit set of the null set. And that comes from the theorem that in ZF, in higher order, if you represent ZF in higher order object theory, that becomes, this is a property, being an R, such that the null set, I'm omitting subscripts, that is, this has the form in ZF, the null set exemplifies this higher order property. It's a property of relations. So now object theory, oops, what happened here? There we go. I unplugged my laptop. I unplugged my my writing pad. So anyway, that basically you get an analysis not only of mathematical individuals but also mathematical relations. So that was my second point.
Let me add one minor other direction for that in answer to the question, which is this: that yes, this is a limitation. There are several potential extensions that I've played around with for allowing you to count abstract objects, or at least classes of abstract objects. And of course, the most interesting class to count would be the numbers themselves. I do think an extension along those lines is possible. It shouldn't require a further axiom, just another definition or two in the system. And there are a couple of approaches to doing that. It's not clear what what it's going to turn out to be the right way to do that is, but I do expect and hope that we will add that in at some point.
Okay, thank you.
Yeah, good question.
Okay, fine. Any other questions? So then I think it's time to applaud and thank our guests. Thank you very much.
Thank you. Thank you. That was fun.
Look, Marcelo, you want to say something? No. Let me just invite Italo Marcelo to reconnect again, because I would like to take the opportunity to discuss a couple of very short matters, if you can.
Okay. Thank you. Thanks for having me. Thank you for inviting me. Bye-bye.
Thank you for coming. Thank you, Uri, for coming, for participating.
Analistas, importante dele, aqueles